Good morning, everyone. Good morning to respected Dr. Paresh Patel, sir, beloved lecturers, and dear students. Myself, Khushbu P. Desai, Assistant Professor from Department of Chemistry, and on behalf of KBS and Natraj College, I welcome you all. Dear participants, welcome you all for an exciting session on photochemistry. I extend my warm welcome to respected Dr. Paresh Patel, sir. Thank you very much, sir, for accepting our invitation to expertise your knowledge to the students. Now, I request Mr. Abhishek Patel to give brief introduction of today's resource person, Dr. Paresh Patel. Over to you, Abhishek Patel.
Thank you, ma'am. It is a great honor and matter of pride to introduce our eminent keynote speaker, Dr. Paresh S. Patel. He has been working at the Post-Graduation Department of Chemistry, Veer Narmad South Gujarat University, Surat, and presently holds the post of professor. He received his master's and PhD in organic chemistry. Sir has 24 years teaching experience in the field of chemistry and he specialized in organic chemistry, reaction mechanism, pericyclic reaction, photochemistry, natural product rearrangement, and molecular symmetry, and many more subjects. His research interest includes synthetic organic chemistry, dyes, drugs, and polymers. He has published about 51 research papers in various reputed national and international journals. Recently, he is supervising six research scholars, while seven candidates have completed their PhD research under his guidance. He has served as investigator of a major research project funded by the University Grant Commission India. Sir is serving as a life member of the Indian Chemical Society and Indian Council of Chemists, and he is also serving as member of boards of Studies School of Science at PP Savani University, Surat. Sir also has delivered many invited talk expert lecture at various universities in Gujarat state. He served as a resource person in one-day workshop under Odisha KCG Education Department Government of Gujarat. Dr. Patel's Dr. Patel has also been judged at national, international, and state level conferences and seminars. Thank you very much, sir, being with us and providing your valuable time with us. Thank you, sir.
Good morning, Kushbu Madam, Abhishek sir, and my dear students. So first of all, I am very, very thankful to the principals of KBS College for inviting me to deliver a session and share my views to my students regarding the photochemistry. Uh, so thank you very much, and thank you very much, head of the department, chemistry department of KBS College, Kushbu Madam. Uh, Dear students, today we are going for the uh, one unit in paper number 2, photochemistry. The syllabus of this unit is photochemical energy, molecular energy, electronic excitations, energy transfer, laws of photochemistry, photochemistry of carbonyl compounds, Norris type 1 reaction, Norris type 2 reactions, photoreduction, Patrone-Bucci reactions, photochemistry of cis-trans isomerisms, photochemistry of butadiene systems, and photochemistry of enone-dienone systems, and photochemical rearrangements. Okay, so dear students, first of all, we are going for the photochemistry, the study of the reaction caused by the absorption of light, that is electromagnetic radiation, is known as photochemistry. So classical example of photochemistry is the conversion of carbon dioxide plus water with chlorophyll and sunlight, or we can say electromagnetic radiation, to give C6H12O6 plus oxygen. That is important. If you balance the equations, so 6 moles of the carbon dioxide, 6 moles of the water to generate 6 moles of oxygen. So this is the classical examples of the photochemistry. The study of the chemistry caused by the absorption of light is known as a photochemistry, and this is the photochemical reactions. Now, according to the Chapman, photochemistry is the science arising from the applications of photochemical methods to the organic chemistry. This is the definition of the photochemistry by Chapman. Now, energy of molecules. Energy of molecules. We know that total energy of molecule is composed of E total is equal to E electronic plus E vibrational plus E rotational and plus E translation energy. So energy of a molecule, it is a composed of electronic energy, vibrational energy, rotational energy, and translation energy. Out of them, the value of translation energy is very, very less, and it is less than 4%. So we can neglect the value of E translation energy. So total energy of the molecule can be represented by E total is equal to electronic energy plus vibrational energy and plus rotational energy. So this is the energy of a molecule. Now, energy of a molecule depends on the property of the molecules, that is like a size as well as shape, flexibility, as well as the type of the motions. Now, on the basis of energy given to the organic reactions, on the basis of the energy given to the organic reactions can be classified into two main categories. One is thermal reactions, and second one is the photochemical reactions. Now, what are thermal reactions? We know that those reactions are carried out by giving temperature in terms of the heating are known as thermal reactions, as for example nitration, sulfonations, alkylation. These are the classical examples of thermal reactions. If you go for the chlorination, if you go for the methylation of benzene in presence of anhydrous aluminum chloride to give a toluene, this is the classical examples of the thermal reactions. Now, what are photochemical reactions? If we applied electromagnetic radiation to the molecule will excite without affecting the surrounding system of the molecule. So that is known as photochemical reactions. Now, in case of the photochemical reactions, we can measure the energy for the photochemical reactions can be represented by E is equal to NH mu is equal to NH mu can be represented by NHC by lambda. We know that E is equal to energy per molecule, H is equal to Planck constant, and value for the Planck constant is equal to 6.63 into 10 raised to minus 27 argon second. C is the velocity of light, and value for the velocity of the light is equal to 3.0 into 10 raised to 10 centimeter per second, and lambda is equal to wavelength. So with the help of this equation, we can calculate the photochemical energy for the reactions. And with the help of this equation, we know that we can go for the IR radiation. So we can derive up to 1 to 10 kilocalorie per mole from IR radiation. If we go for the visible region, then we can derive up to 38 to 71 kilocalorie per mole. That is from visible region. And from ultraviolet region, we can derive up to 143 kilocalorie per mole. Okay. So if we applied electromagnetic radiation to the molecule will excite and will go into upper excited state without affecting the surrounding system of the molecule. So these are known as the photochemical reactions. We already discussed about the one classical examples of the photochemical reactions, that is the conversion of carbon dioxide to the carbohydrates plus oxygen. Norris type 1, Norris type 2, Paton-Bucci reactions, dimerization of the butadiene, photoreductions of benzophenone to benzphenol. These are the classical examples of the photochemical reactions. Now, next title is the Next title is the electronic excitations. Now we know that orbital E is the energy. Orbital can accommodate a pair of electron and combination or overlapping of two atomic orbital to generate molecular orbital, in which a lower energy contained orbital, which is known as a bonding orbital, and the higher energy containing orbital can be represented as an anti-bonding orbital. Now, in ground state conditions, bonding orbital consists pair of electrons, and anti-bonding orbital remains as it is, that is vacant in the ground state condition. Now, if we apply electromagnetic radiation to the molecule, this molecule will excite and electron will go into upper excited state. So this is known as electronic excitations. So repeat again. Any stable organic molecule or orbital consists of pair of electron in a outer orbitals. In a ground state condition, we can say the lower energy contained orbital consists of pair of electrons. If we apply the electromagnetic radiation, this molecule will excite, or we can say electron will excite into and will go into upper excited state. This is known as a electronic excitation. Suppose this one is the sigma bond. So these electronic excitations can be represented as sigma sigma star electronic excitations. If pi bond is there, so that type of the electronic excitations can be represented as a pi pi star. Similarly, sigma pi star and pi star electronic excitations can be possible. Now, in case of the butadiene system, E is the energy. Butadiene consists a pair of electrons. Suppose this one is the psi 1. This is known as psi 2. psi 3 and psi 4. This is ground state conditions. Okay, in ground state condition, this is excited states. These are known as a bonding orbitals, and remaining is the anti-bonding orbitals. Okay, if we applied electromagnetic radiation, so what will happen? This electron will go into upper excited state. So this type of the electronic excitations can be represented as a pi to pi star electronic excitations. So this can be represented as pi pi star electronic excitations. Benzophenone can give absorbance log E log left side, and this is the absorption, or we can say lambda. Now, two maxima can be observed in case of 245 nanometers and 345 nanometers in case of benzophenone. This is benzophenone. Benzophenone can give two electronic excitations or two maxima, one at 245 nanometers, another one at is 345 nanometers. Okay, now this corresponds to pi pi star electronic excitations, and this corresponds to n pi star electronic excitations. Okay, so carbonyl compounds can give two maxima, or we can say benzophenone can give two maxima, one at 245 nanometers and 345 nanometers. So this 245 nanometers, which corresponds to pi pi star electronic excitations, and 345 nanometers, which corresponds to n pi star electronic excitations. So anyhow, carbonyl compound can give two types of the electronic excitations. One is n pi star, another one is pi pi star electronic excitations. Now, these two states are the most important photochemistry: singlet states and triplet states. This is the bonding orbital, and this is anti-bonding orbital. Any stable organic molecule consists a pair of electrons in an outer orbital, and this can be represented as S0. Okay, this is E is energy, and these are the different states, that is singlet state. Okay, so dear students, any stable organic molecule consists pair of electrons in a outer orbitals, so that can be represented as S0. This is known as a ground state condition of the stable organic molecule. Now, if we applied electromagnetic radiation, so what will happen? Molecule will excite, or we can say electron will excite and will go into upper excited state without spin inversion. So this state can be represented as a singlet state. Suppose this electron will excite into anti-bonding orbitals, so these states can be represented as S1 state. This is singlet state S1. So different singlet state can be possible S1, S2, S3, S4, etc. So what is singlet state? If we applied electromagnetic radiation to the stable organic molecule, molecule will electron will excite into upper excited state without spin inversion. So this state can be represented as a singlet state. Now, if we apply electromagnetic radiation to the molecule, molecule will excite and with spin inversion. So this state can be represented as a triplet state. So different triplet states can be possible T1, T2, T3, T4, etc. So dear students, what is S0? S0 is the ground state containing stable organic molecule, which consists of pair of electron in the outer orbitals. If we applied electromagnetic radiation to the molecule, molecule will excite or electron will excite into upper excited state without spin inversion. So this state can be represented as a singlet state. If we apply electromagnetic radiation, electron will excite with spin inversion. So these states can be represented as a triplet states. So this is the most important in the photochemistry. What is the S0? Singlet, what are singlet states and what are triplet states? Now, next title is the Jablonski diagram or modes of dissipation of energy or principles of the photochemistry. Okay, now we know that one stable organic molecule consists of one stable organic molecule consists of three pairs of the electrons in the outer orbitals. If we applied electromagnetic radiation, so what will happen? This is known as S1, S2, T1, T2, etc. This is known as intersystem crossing. This is known as internal conversion. This is again internal conversion. This is intersystem crossing. Okay, dear students, one stable organic molecule consists outer orbital consists three pairs of the electrons. If we applied electromagnetic radiation to this stable organic molecule, so what will happen? So one electron will go into upper excited state without spin inversion. So these are known as a singlet state. So different single state can be possible: S1, S2, S3, S4, etc. And if we applied electromagnetic radiation, molecule will excite or electron will excite and will go into upper excited state with spin inversion. So this is the spin inversion. So these states can be represented as a T1, T2, T3, T5, etc. So intersystem crossing. So what is intersystem crossing? That is we will discuss later on. But intersystem crossing is the spin inversion, electronic excitations with spin inversion. Now these are the internal conversions. Okay, if we applied electromagnetic radiation to the molecule will excite into upper excited state, and that molecule will, after that, will come down into the ground state by emitting of the photons or energy. So different internal conversion can be possible, just like a S4 to S3, S3 to S2, S2 to S1, and S1 to S0. Out of this internal conversion, S1 to S0 takes longer time. It takes 10 raised to minus 9 to 10 raised to minus 6 seconds. And this is known as a fluorescence. This is known as a fluorescence. Okay. All excited states can be converted into the ground state condition. So internal conversion can be possible: S3 to S2, S2 to S1, S1 to S0. Out of this all internal conversion, S1 to S0 takes a longer period, means this is the rate determined state, and this state can be represented as a fluorescence. Now S1 to T1, this is the energy gainful reactions. Similarly, through intersystem crossing, similarly S2 to S3, S2 to T3, T2, S3 to T3. Now internal conversion again from T3 to T2, T2, T1 to T3 to T2, T1 to, and finally T1 to R0. This is known as phosphorescence, and phosphorescence takes 10 raised to minus 1 to 10 seconds, 10 raised to minus 3 to 10 seconds. So again, T1 to S0. This is known as a phosphorescence, and it takes 10 raised to minus 3 to 10 seconds. Okay, so dear students, internal conversion from T3 to T2, T2 to T1, and finally T1 to S0. Out of them, T1 to S0 takes 10 raised to minus 3 to 10 seconds. Means this is again phosphorescence. So fluorescence takes 10 raised to minus 9 to 10 raised to minus 6 seconds, and phosphorescence takes 10 raised to minus 3 to 10 seconds. It takes more time. So phosphorescence is faster than fluorescence. So why phosphorescence is faster than phosphorescence? This is the reason behind it. It takes 10 raised to minus 9 to 10 raised to minus 6 seconds, and phosphorescence takes 10 raised to minus 9 to 10 seconds. Now, the energy transfer from excited triplet to singlet state, which is possible if the energy difference between that singlet state and triplet state is minimum 5 kilocalorie per mole, then 100% energy transfer can be possible. So this is known as a Jablonski diagram, or modes of dissipation of energy, or principles of the photochemistry, or why fluorescence is faster than phosphorescence. So this is the answer of these questions. Now next title is the energy transfer. So why energy transfer is required, or what is energy transfer? Energy transfer means uh, one triplet molecule can transfer energy to the singlet molecule to gain or to give a triplet state of the molecule. So this is energy transfer. But why energy transfer is required? In case of the butadiene, we know that butadiene, and we also know about dimerization of the butadiene. So dimerization of the butadiene with the help of electromagnetic radiation can be possible if the triplet state of butadiene is obtained. Then and then dimerization of butadiene is possible. So dear students, if we go for the dimerization of butadiene in presence of electromagnetic radiation, we need a triplet state of the butadiene, and we can't get the triplet state directly by irradiating of electromagnetic radiation. Okay, so if we applied electromagnetic radiation to the butadiene system, we can't get the triplet state directly. First of all, we can get a triplet state of butadiene only. Then energy transfer from triplet photosensitizer to singlet butadiene system. This is known as energy transfer. So why energy transfer is required? So as for example, butadiene. For the dimerization of the butadiene, we need a triplet state of the butadiene. If we apply the electromagnetic radiation to the butadiene system, we can get only a singlet state of the butadiene only, and we can get only a cyclized product with the help of the butadiene system. We can't get the triplet state, we can't get the dimerization of the butadiene with the help of the singlet butadiene. So in this case, we need a energy transfer. As for example, suppose one donor molecule, if we applied electromagnetic radiation to give first a singlet state, and with the help of intersystem crossing to give a triplet states, then energy transfer from the triplet donor to one acceptor molecule to give a triplet acceptor and donor. Okay, if we apply electromagnetic radiation to the donor molecule, it will go into a singlet state and corresponding triplet state. Now, energy transfer from triplet donor to acceptor molecule. So, acceptor molecule will gain a triplet state, and donor molecule will gain a singlet state. So, with the help of this concept, if you go for the benzophenone, if we mixed butadiene, benzophenone with the butadiene, so what will happen? So, benzophenone will excite. If we apply the electromagnetic radiation to give a singlet state of the benzophenone, and through intersystem crossing to give a triplet states of the, and then energy transfer from triplet benzophenone plus butadiene to give a triplet butadiene plus singlet state of benzophenone. So this concept can be recognized as energy transfer. So why energy transfer is required? As for example, butadiene, we can't get the triplet state of the butadiene directly with the help of electromagnetic radiation. So we need a photosensitizer. So benzophenone can act as a photosensitizer. So first, benzophenone can transfer into singlet state of the benzophenone and through intersystem crossing to give a triplet state of the benzophenone. Now, benzophenone can transfer energy from triplet benzophenone to singlet butadiene to give a triplet butadiene. Now, dimerization of butadiene can be possible now from triplet state of the butadiene. Now, here one condition is there: if the energy difference between this triplet benzophenone and singlet butadiene system is 5 kilocalorie per mole, then the 100% energy transfer can be possible. The energy difference between triplet benzophenone and singlet butadiene is minimum 5 kilocalorie per mole, then approximately 100% energy transfer can be possible. Now we know that the energy for the benzophenone triplet is just near about 65 to 66 kilocalorie per mole, and butadiene consists 60 kilocalorie per mole. So nearer about 5 to 6, the difference between these two states is approximately 5 to 6 kilocalorie per mole. So here approximately 100% energy transfer can be possible in this case. So this is known as a energy transfer. Quantum efficiency can be represented as number of molecules reacting in a unit time and number of quanta or energy absorbed in a unit time. The ratio of numbers of the molecule reacting in a unit time divided by numbers of quanta absorbed in a unit time, this ratio can be represented as a quantum efficiency. In most of the cases, the value of quanta is less than 1.0, but in due to the some side reactions, impurities, etc., but in case of the chain reactions, the as for example chlorination of methane or reactions of chlorine and hydrogen to generate hydrochloric acid, that is the chain reactions, and that chain reactions is 10 times 6 to 10 raised to 6 to 10 raised to 7 times faster. So in that case, this is the limitations of this quantum efficiency. So anyhow, quantum efficiency is the ratio of numbers of the molecules reacting in a unit time and numbers of the quanta absorbed in a unit time, and the value of quantum efficiency is always less than 1.0 except the chain reactions. Now, laws of the photochemistry. Two laws are the most important in the photochemistry. First law, first one is first law, or we can say this is known as Grothaus-Doppler's law. So two laws are the important for the photochemistry: first law and second law. First law, or we can say Grotov-Stopper's law. Now, what is Grotov-Stopper's law? When light radiation fall on a substance, only fractions of incident light can be responsible for the chemical transformations. There is no role of the reflected energy as well as transmitted light. Okay, so what is first law or Grotov-Stopper's law? When light radiation fall on a substance, only the fractions of incident light is responsible for the chemical transformations. There is no role of the reflected as well as transmitted light in the chemical change. So only incident light is responsible for the chemical transformations. Second law, or we can say this is known as Einstein's law. Now, what is Einstein's law? This law states that each molecule or atom activated by the light absorbs only one quanta of light. This is known as the Einstein law or Einstein-Stokes law. This is Einstein-Stokes law. So, what is second law or Einstein-Stokes law? Each molecule or atom activated by light absorb only one quantum of light, which cause activations. So, AB plus electromagnetic radiation. This is one molecule and one photon to give excitations. So this is the second law. Okay. So two laws are the important in case of the photochemistry: first law or Grotov-Stopper's law, second law or Einstein-Stokes law. These are the two laws of the photochemistry. Now next title is photochemistry of carbonyl compounds. Carbonyl compounds, mainly ketones, usually undergo radiation, electromagnetic radiation, to give two types of the electronic excitations. One is n pi star, another one is pi pi star. Okay, out of them, 285 nanometers and 180 nanometers, these are the electronic absorption for the ketones. So anyhow, this is the carbonyl compounds. This is the one carbonyl compound. In case of the carbonyl compounds, we know that the electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1. In an electronic excitations, 4 electrons are unpaired in the carbon. Similarly, in case of the oxygen, 1s2, 2s2, 2px2, 2py1, 2pz1. Out of them, one electron of carbon and oxygen atomic orbitals are involved in the formation of the pi bond, as well as one electron from the carbon atomic orbital and one electron from the oxygen orbital is occupied in the formation of the sigma bond. So two electrons remains as it is, that is in the help of the p orbital of the oxygen atom. And these two electrons can be recognized as n-pi electrons, and these are the responsible for the electronic excitations in the carbonyl compounds. So two types of the electronic excitations can be possible in case of the carbonyl compounds. One is n-pi star, another one is pi star. So this is the photochemistry of carbonyl compounds. So first examples of the photochemistry of the carbonyl compounds is the photoreduction. Now, what is photoreduction? We know that what is reduction? Addition of hydrogen, removal of oxygen. That is known as reduction. Over here, the reduction of benzophenone to benzphenacol. This is known as benzphenacol. So here, addition of the hydrogen. So this is reduction. Reduction of benzophenone to benzphenacol with isopropyl alcohol with electromagnetic radiation, or we can say at the 345 nanometer, is known as photoreduction. And this is the oldest example of the photoreduction. So now, what is photoreduction? The reduction of benzophenone to benzphenacol with or in isopropyl alcohol with the help of electromagnetic radiation can be represented as a photoreduction. Now, first step of this reaction mechanism, okay, in a mixes of benzophenone and isopropyl alcohol, only benzophenone can excite into singlet state and the triplet state. That is the first step of this reactions mechanism. Now, reaction mechanism of this reactions, first step is the if we applied electromagnetic radiation to give a singlet state of the benzophenone, and through intersystem crossing to give a triplet states of the benzophenone. This is the first step of this reaction mechanism. Now, second step, what will happen? This triplet benzophenone plus isopropyl alcohol. Now, the nature of the the nature of the triplet benzophenone, just like a alkoxide. And we know that the nature of alkoxide, which can abstract proton very quickly. So the triplet state of the benzophenone, which is very resemble to alkoxide. Alkoxide means a nucleophile, and the characteristics of the nucleophile which can abstract proton very quickly. So in this one, the structure of the benzophenone, triplet benzophenone, can abstract one proton from isopropyl alcohol. So what will happen over here? C6H5 twice COH. This is known as a free radicals, and this is known as benzophenone ketine. Plus, now here methyl group, methane group, OH group, and methyl group. So this triplet benzophenone can abstract this hydrogen. This is very reactive than other hydrogens. So to give CH3 twice COH. This is again free radical. So this is known as acetyl ketine, acetone ketine. Okay. So first step is to get the triplet state of the benzophenone. Second step of this reaction mechanism, this triplet benzophenone can abstract one hydrogen from the isopropyl alcohol to give benzophenone ketine and acetone ketine. Now in the next step, two moles of benzophenone ketine to give benzphenacol. After completing this reaction mechanism, the value of quantum efficiency is just nearer about 1.0. After completing this reactions mechanism, the value for quantum efficiency just near about 1.0. It means the benzphenacol, so benzophenone ketine, can't react in the further steps. So we have to go for the phrase triplet benzophenone. Plus, remaining portion is the acetyl ketine. So now again, we know that the conditions, the characteristics of the triplet benzophenone, which can abstract proton from the acetone ketine to give again this is benzophenone ketine plus this is nothing but the acetone CH3 C double bond O CH3. Now, last step of this reaction mechanism is the combination of 2 moles of benzophenone ketine to give benzphenacol. So, dear students, this is the photo reduction of benzophenone to benzophenacol. Now here, abstraction of protons from the isopropyl alcohol. So this reaction mechanism can be recognized as intermolecular hydrogen abstraction reactions mechanism. Why? This photoreduction can be carried out with the help of isopropyl alcohol. It means hydrogen abstraction can be carried out from isopropyl alcohol. So these reactions mechanism can be referred as intermolecular hydrogen abstraction reactions mechanism. So exam point of view, we have to remember that give the reactions mechanism of intermolecular hydrogen abstraction reactions mechanism. This is nothing but the photo reduction. Now, if these photo reductions can be carried out in benzophenone, benzhydral, then what will be the product? If you go for the reactions of this is benzophenone plus benzhydral. This is benzhydral in presence of electromagnetic radiation to give C6H5 twice COH. Benzphenol only. So first step will be the same, singlet state and the triplet state of the benzophenone. Now this triplet benzophenone can abstract one proton from the benzhydral. This is known as benzhydral. Now we know that the characteristics of the triplet benzophenone, which can abstract proton from the benzhydral. So here phenyl group, and OH group. So this triplet benzophenone can abstract one proton from this methane group to give, this is known as benzophenone ketine. And last step, combination of 2 moles of the benzophenone ketine to form a benzphenol. So if you go for the 2 moles of benzophenone ketine to give benzphenol. This is the reactions mechanism. Now, if these reactions can be carried out in toluene, to give benzophenone plus dibenzyl. This is known as dibenzyl. Okay, so photoreduction of benzophenone in toluene with electromagnetic radiation to give a benzphenol plus dibenzyl. So first step of this reaction mechanism will be the same. First step is to excite benzophenone into singlet state and triplet state of the benzophenone. This is the triplet state of the benzophenone, and we know that the property of benzophenone ketine, triplet benzophenone can abstract one hydrogen from toluene to give C6H5 twice COH. This is known as benzophenone ketine plus this is known as benzyl ketine. Now combination of 2 moles of benzophenone ketine to give benzophenacol, and 2 moles of benzyl ketone to form dibenzene. So, dear students, photoreduction is a intermolecular hydrogen abstraction reactions mechanisms. Hydrogen can be abstract from the solvent, maybe isopropyl alcohol, maybe toluene or benzhydral. So I think this is the enough for today's discussion. So thank you very much, Kusbu madam, for providing me this platform. So we will meet on the next session. So thank you very much, dear students, for listening me very silently. Thank you very much.
Thank you, sir. Thank you very much, sir, for facilitating such a positive learning environment with exam oriented guidelines. We really enjoy your lecture, sir. And dear participants, we will be back soon with upcoming webinar on this topic. So, goodbye, everyone. Have a nice day. Thank you,
Thank you.
sir.
Thank you.
Goodbye, sir.
Thank you.